This is the video for section 4.2, which is all about the formulation of mathematical statements. I have a couple more pieces of notation to show you, and then we'll look at some mathematical statements, including lots of warnings about things that might go wrong and some examples of things going wrong. Let's meet the notation first. It's a sort of shorthand, really, that I want to show you for the phrases for all and there exists. And this is used absolutely all over mathematics, so we've really got to learn these symbols, and I think I encourage you to use them as well. So here's the first one I want to show you. It's this sort of upside down A, which I draw by writing a V and then putting a horizontal line across it. And that means for all, or for each, or for every, and can be used as a shorthand for those words. So whenever you would use those words, you are allowed to write this symbol instead. And also, we've said there exists quite a lot of times. There's a symbol for that as well, which I guess I draw by doing a sort of square bracket and then a line through the middle. That means there exists, and it replaces those words. These are known as quantifiers, and they're used to make claims about members of sets or other objects. The symbol there exists is often followed by some sort of claim about the element that you're saying it exists and satisfies some property. You're probably not just telling me that your set contains an element, you're probably telling me something about such an element. Maybe it's the smallest in your set, maybe it's a prime number or something. Well, let's find out. So often the statement there exists X in your set is followed by some property that is satisfied by X. And at this point I'm just going to encourage you to leave a space maybe, or maybe put a comma between these. So saying there exists X in the set such that the property P of X holds. Some people write out the words such that in between just to make it extra clear that you're saying there exists X in the set S such that this property holds. I prefer to write just ST in the middle for such that. So putting it together then, I would read this as there exists X in the set S such that P of X is true. It's a prime number. There exists X in the naturals such that X is prime. A true fact, I think. Natural numbers does contain primes. So I'm going to use ST. That's not quite mathematical notation so much as an accepted shorthand that stands for such that, and I'm using that a few times in the next few slides. So that's what I mean. But in other places, you might be lucky to get anything there. The word such that ST, or just a space or comma that's saying we've set this up now, and here's what's true about that. We'll see some examples of that later on. Okay, one more. There's a variant of there exists where people put an exclamation mark immediately after the symbol to say there exists unique, which means that there's one element and only one element with the given property. So I might say there exists a unique X in the natural numbers such that X squared is equal to 4. I think that's actually a true fact because the number 2 is in the naturals and the number -2 is not in the naturals. So I'm making the claim that there's a unique X in the naturals with that property. You don't have to use this. If it happens to be unique, you're not in trouble for not writing the exclamation mark. This is a sort of stronger claim, and you're not required to always make the strongest claim that you can. So you are allowed to ignore this and never use it. But if you see somebody else using it, here's what they mean. They're telling you both that this element exists and that it's the only one in the set. There might have been some other conditions that were set up, but now we have a unique element. Right, okay. Personally, I don't use this one very much because I already use exclamation mark quite a lot in the rest of my writing, so I'm saving it for emphasis and factorials. And if I have to say that something's unique, I then have to say it in words, but you're welcome to use this one if you like. So using these symbols, we can build statements. So here are a couple of examples. This one says, for all x in the reals, x squared is greater than or equal to 0. And notice that in this one, there's just a space, not even a comma to separate those two parts of the claim. But there exists an x in the complex numbers such that x squared is negative. There exists the number 3 times I in the complex numbers that squares to -9. You should read this as for all x in the reals. We just read it out while looking at it. I want you to notice the such that over here. I want you to notice the structure on this one, for all at the front, and then the claim. I want you to notice that this one has a statement there exists at the front, and then the property about x afterwards. That's a general rule about when you're allowed to say x. Let's see the definitions of injective and surjective functions written out using this notation. So putting things together, we have for an injective function, our definition was all about collisions, remember? If f of x1 is equal to f of x2, then x1 is equal to x2. And this can be written like this. So at the front here, there's some conditions. For all x1 and x2 in x, that's a very permissive condition, right? You can take any elements x1 and x2 from the set x. And then here's the claim about those numbers. The claim is all of this, that f of x1 equals f of x2 implies that x1 equals x2. And this is a good example of implication, I think, because for an injective function, we're not claiming that f of x1 is equal to f of x2. We're not making a claim that p is true, or in this statement of the form p implies q. That'd be quite a strong statement. I think that would say the function is constant if you're going to insist that f of x1 is always equal to f of x2. We're saying that if f of x1 is equal to f of x2, which might or might not be true, then x1 is equal to x2. We're making no claims about what happens if f of x1 is not equal to f of x2. Either way. In fact, I think for an injective function, I suppose if x1 is equal to x2, then the function can only take one value. So I suppose that those are equivalent, if and only if in there. If x1 is equal to x2, then f of x1 has to be equal to f of x2. But the important half of the implication is this one in the definition here, that if the values of the function are equal, then x1 has to be equal to x2. I've also written out the definition of a surjective function. So remember, surjective is about reaching everything in the codomain. So it says, for all y in y, there exists x in x such that f of x is equal to y. The value of that value of x, if you evaluate the function there, you get that value of y. And this is, I guess, an important point to make, that as you read inwards, the value here of x is allowed to depend on the value of y. So here we say for all y and y, start of the story, and then we say there exists x, and implicitly here, it's allowed to depend on y. Occasionally you might see people spell that out by writing a kind of subscript on the x, or writing some x that depends on y in words. But in general, it's always the case that elements introduced in here, if you're saying that there exists something, it's allowed to depend on variables that you'd already set up to the left. And the order of these statements really matters. Okay. A couple more statements of this form. I've got a complicated way of saying that every prime number greater than 2 is odd at the start, where blackboard P, how would I write that? I'd probably write it like that, I suppose, is the set of all prime numbers. That's not standard. That's not one of the letters that you're expected to remember. But we already use blackboard N, Z, Q, and R, so I thought for the set of prime numbers, maybe we'll use blackboard P. Anyway, for all primes, which I've written as for all P in set P. And then I've written this out as, if P is greater than 2, then P is odd. So this bit over here, there's an implies sign here. So I say if P is greater than 2, then. And then all of this is a slightly silly way of saying that P is an odd number. We'll get to that in a moment. Notice that I have to glance ahead. I have to see that there's an implies sign coming when I'm reading this out, so that I know to say if, then. The implies symbol captures both the if and the then. And you might prefer a different way of reading that out. So you might prefer the phrase only if in the middle, where you say P is greater than 2, only if P is odd. But for me, that feels a little bit backwards. Somehow these are all equivalent ways of saying the same thing, but for me that feels slightly backwards. I'd like to maintain the idea of things moving forwards. Anyway, we saw 9 different ways of reading out an implies symbol, so you can choose whichever one you like. Anyway, the underlined section is about the number P being odd, and I have there the claim that there exists n in the naturals such that P is 2n plus 1, and that's a way of saying that P is an odd number. And notice again here that the number n is allowed to depend on P because P was introduced first, and then after that n is allowed to depend on the things already introduced in that order. Down here the statement says for all x in the set of reals, and then there's a big claim, x is negative, or there exists y in the reals such that y squared is equal to x. So this is capturing the idea that all real numbers are either negative or there's something that squares to give you that number, which we might call a square root in the reals. And this is a claim that such a number exists. It doesn't give us any way to find such a square root or calculate it to 10 decimal places or do anything with it really. This is just the claim that such a thing exists. There's a little bit of moving around going on down here where I say every non-negative real number, because of course we could capture that in a different way. If we wrote this set with the reals, if we wrote out the set modified with some set difference to take out the negative numbers, we could make the claim over there about y. There are often different ways to write down the same statement. We've already seen a few different ways to talk about the statement. We've seen the contrapositive, I suppose. So we've seen ways to manipulate statements. Which one you write down, I think, depends on how you're thinking about the statement and how you're thinking about the claim that's being made. But you should maybe be able to think of other ways to move things around as well. Okay, so I could talk about x being in a different set. Okay, so I want to really reinforce the idea that changing the order of the symbols matters. I have my example again with S being the set of students at Oxford and C the set of colleges. So we can say for all students in the set of students at Oxford, okay, so for all Oxford students, there exists C in the set of colleges. Okay, so there exists a college such that that student is a member of that college. We're being a little bit cute here, I think. Well, I suppose the set of colleges is a set of sets, let's say. Is a college a set? Well, never mind. It is for this example. Okay, so this says, for every student, there is a college of which that student is a member. So it's got the setup at the front here. If you mix up the order of the statements, then you could build a statement like this, which says there exists a college in the set of colleges. Okay, so there exists a college such that for all students at Oxford, that student's a member of that college. That'd be the case if you were all at the same college. If there exists some particular college such that every student's at that college. Which is the situation, I believe, for Trinity College Dublin, where every student is at the same college. It's a different claim, though, where at the top we have this idea that everyone is at a college, not necessarily the same one, and at the bottom we have this idea that everyone is at the same college. Those are different claims, and Once you've used the symbols to write them down, they look pretty similar. This notation is powerful, but also a little bit dangerous, that it lets you write down statements that are different, that are not logically equivalent, using the same symbols in a different order. So we have to be careful for that as well. So we always, just to say it one more time, we always read from left to right, and new elements that are introduced are allowed to depend on the previously mentioned elements, but they can't depend on things that we haven't talked about yet. If you like computer science, then perhaps you've met ideas that variables can depend on existing variables, but they can't depend on things that you haven't defined yet as you go through your program. Something similar is going on here. Okay, let's talk about negation to write down the negative of a statement like the ones we've been looking at. So if your statement starts, for all x in x, some property is true. It says that the property is true for all of them. The negation of that, the opposite, would be there exists an x in x such that the property doesn't hold, not p, for that value of x. So that's the opposite. And then, interestingly, if your statement is of the form there exists an x in x such that p of x is true, so you're just saying there exists some value of x such that the property holds for that value. The opposite of that one is, well, for all x in x, not the property. I checked all of them and it doesn't hold for any of them. So that's the negation of the statement. There exists something in there where it holds. So when you look at these, you might notice that exists and for all kind of switch roles when you negate a statement, and it's better than that because p of x might itself be a complicated statement which involves some for all symbols and some exist symbols. So we can work out the negation of quite a complicated statement by working our way inwards. This is the rule for the outermost for all, or the outermost there exists. Let's work our way in. So let's take that statement we had before. For all students at Oxford, there exists a college in the set of colleges such that the student is a member of the college. Colleges is still a set of sets, which I still find a little bit funny. Okay, so working outside in lets us negate this statement. So let's say we're trying to disprove this. Trying to do some sort of proof by contradiction, perhaps. And we're trying to work out what the opposite would be, the negation of this statement. So the easiest way to negate it is just to put not at the front, to say it's not the case that for all students at Oxford there exists a college such that the student is at that college. Fair enough. But we can start to move that inwards by identifying, to start off with, I want to look at the way this statement is structured for all s in s, and then some more stuff, which I'm going to read in a second. But if I say that that's p of s, in the green brackets, some property of s, a property of the student. It's not a property of the college because we haven't mentioned the college yet. The college is sort of a dummy variable in this. Anyway, never mind. So I have some property of students. If you do that, then, well, we know how to negate this initial for all s in s. The way we negate that is we write there exists s in s such that not the statement about students. So I've kept the statement there, and I have a not symbol out the front now. But now we can keep going because if I highlight this statement in here, in purple brackets, maybe that could be a property of, and that's a property of the student and the college. So the way you negate a statement of this form, which says there exists C and C such that some stuff, is that you write for all C and C, it's not the case that that is true. And at this point, S is fixed. We're inside some sort of wider brackets where we're talking about a particular student. So I have that statement which depends on S, but it's a fixed S at that point of the statement. Okay, so then finally I have the claim down here, not student is a member of the college, which we might write as student is not in C. And in words, if I were to read these out, I might say the first one is, it's not the case that for all students at Oxford there's a college that the student is a member of. For the second one, I might say there's a student at Oxford such that it's not the case that there's a college that student's a member of, which is still a little bit convoluted. Down here I might say there's a student at Oxford such that for all colleges at Oxford it's not the case the student's a member of that college. we looked at all colleges. And that last line I might read as there's a student at Oxford such that for all colleges they're not a member of that college. And the thing I'm trying to avoid saying is something closer to there's a student who's not a member of any college, which turns around the order of the clauses, because that sort of thing is dangerous. English language is a bit tricky sometimes, so just try to pass these as English language sentences. Occasionally in English, or just in your thought process, or possibly out loud in a tutorial meeting or something like that, you might say things in the order that they come to you. So you might say, for all natural numbers x, x is less than y for some natural number y. And depending on where you put the pauses, that could mean a couple of different things. It might mean for all x in the naturals, there exists y in the naturals such that x is less than y. Fair enough. Or it might mean there exists y in the naturals such that for all x in the naturals, x is less than y. And in symbolic notation, if we want to write down the one of those statements that's true, we should write down for all x in the naturals, there exists a y in the naturals such that x is less than y, with the quantifiers in that order. It's a tendency when you're talking out loud to put an important quantifier, I suppose, at the end of the sentence. And mathematicians try to avoid this when writing down logical statements, although we're not perfect, and it's quite common to put a for all at the end of a statement. I've done it a few times in these videos and in the lecture notes to say for all x right at the end. But best practice is to get things in the correct order, even if it's not the order that you thought of all of these terms and conditions along the way. Okay, so English language, a little bit tricky. Clauses can matter. If you're saying something like this out loud, then it really matters whether you pause here and say all of this after that point as one sort of flowing phrase, or if you pause over here. If you pause too long here, then it sounds like the false version. Best practice is to, well, write down what you mean. Okay, using logical notation like this can make your arguments more streamlined. We've got an example on the board here where we show that set equality is the same thing as double inclusion by writing out different statements and messing around with definitions to show all these equivalent things. You've got to be careful with this though. It's powerful but slightly dangerous, as I keep saying, because if you're writing these, the ideas tend to flow in one direction, and it's always tempting to write double-headed arrows. But you need to actually check that the thing you're claiming is, well, true in both directions, that the implications are both true, and if you're presenting an argument, you need to make sure that they're sufficiently obvious in both directions if you're trying to convince somebody that this is true, if and only if that is true. So while it might be true that statements are equivalent, if your job is to convince somebody by showing them related statements, then it's possible to take large leaps and label them, if and only if, and it's possible to be correct about that. But sometimes you might find that your logical leaps are larger in one direction than the other. Anyway, this is an option that you can use notation like this to work through a proof to streamline things, but do be careful, especially if you've condensed things down a lot. In some sense, it makes things harder to follow if you're not careful with the notation, and if your layout is not very strong. Here I've tried to line up all of the double inclusion statements, all of the double implication symbols, so that things line up on the page. That's always a good idea. Okay, right. Finally, I just want to show you some examples of hypothesis and conclusion. Lots of mathematical statements are of the form if P then Q. Fermat's last theorem, right? If X and Y and Z are numbers with these properties, and if N is a number with this property, then this equation has no solutions. So even very complicated maths is sometimes phrased as if P then Q. P and Q can be quite complicated statements, or combinations. P is called the hypothesis and Q is called the conclusion, and it's a good idea when you see a new statement to try to separate out which parts are the hypothesis and which parts are the conclusion. The hypothesis can be quite short, it can be quite long, and the conclusion can be quite interesting, or it can be not interesting. Let's have a look at some examples. So here's a big claim. If n is a non-zero natural number, then n has a unique prime factorization. So there it is. The hypothesis here is just n is a non-zero natural number. And the conclusion is n has a unique prime factorization. So that's an exciting conclusion. The structure here is literally written out as if and then. So there's a hypothesis at the start, which is quite minimal. There are lots of non-zero natural numbers, and there are no further conditions in this case. And then the conclusion afterwards is, well, that n has a unique prime factorization. There it is. Okay, let's see another. So statements are sometimes a little bit harder to pass. So every prime number greater than 2 is odd. And you might like to play around with what that means, find other ways of writing this. One way that you might write it is, let P be a prime number greater than 2, and then P is odd. So this part is the conclusion, that P is odd. And you see it's hard to underline in here, isn't it? Because I think I want to underline something like number is odd. It doesn't have a name in this statement, so it's not obvious which bit to point at. That number is odd is the conclusion. And the setup here, the hypothesis, this idea that we're letting P be a prime number greater than 2. So it's multiple conditions, if you like. P has to be both a prime number and greater than 2. Although we've seen that the combination of two conditions is a single condition, so you can't really count them like that. Okay, as a way of unpacking a statement, so you might meet things like this, where it's phrased in a more concise manner and maybe needs to be unpacked in order to work out what the claim is. So you'll see at some point in the first year, if you do the analysis course, something called the intermediate value theorem, which I've got twice on the screen, once quite badly at the top here. So maybe what I might say out loud. Whenever f is a continuous function on the reals, a and b are real numbers such that a is less than b, f of a should be negative and f of b should be positive, and then f of c is 0 for some c in the interval ab. And that's a bit of a mess if I say it out loud like that. Maybe you noticed I couldn't resist saying then here, just to make it clearer what on earth I was talking about. But printed on the page there, it's really not obvious that the word then goes there, but that comma is where it switches from talking about the hypothesis to the conclusion. And part of the problem is that for some c in that interval, there should be a quantifier there. There exists c for some in that interval. Well, it's not the problem. The problem is not that I'm not using a quantifier. The problem is that the quantifier should come before the first mention of c. What on earth is c when I get to this point of the sentence? It needs to be introduced with a quantifier. So to make this clearer, we need a big then here, and we need to introduce c before we start making claims about it. So here's a better version. which is also more formal about what the function is. Let f from R to R be a continuous function, and suppose that a and b are real numbers are such that a is less than b, f of a is less than 0, and f of b is positive, full stop. Then there exists a real number c in the interval ab such that f of c is 0. This way round I think makes more sense. It's really helped by having the full stop in the middle. So when you're writing your mathematical statements, you do have the option to split them into sentences. And here the first sentence sets out the conditions, the hypothesis for this claim, and the conclusion is in a separate sentence. That's the punchline of the joke, if you like. You have the setup in the first sentence, and then punch. There exists a real number such that f of c is 0. You'll notice that time I read it out and I forgot to give you the conditions on C, but there you go. It's trying to capture the idea that if you have a sign change for your function, then there's a point where your function crossed the x-axis, which is a fact that you might have met in school before. There's a proof of that coming up in analysis in first year for math students. It relies on some understanding of what a continuous function is, which is not a property of functions that we've met in these lectures. Anyway, that's some examples of logical statements for you. In the next video, I'd like to look at examples of proof. We're not going to prove this, we're going to prove some other statements. So I'll see you in the next video.